My name is Guglielmo Grimaldi, and this is the video abstract for the paper Testing Holographic Entropy Inequalities in 2+1 Dimensions by Brianna Grado-White, Matthew Hedrick, Veronica Hubeny, and myself. In the classical limit of the ADS-CFT correspondence, we have a duality between quantum states and smooth, asymptotically ADS spacetimes. Understanding requirements for a quantum state to have a geometric smooth bulk is a very old and natural question in holography. In the past 2 decades, holography has shown us the strong connection between entanglement and geometry, so studying the entanglement structure of holographic states is an excellent starting point to attack the above question. We have learned a lot about static or time reflection symmetric states throughout the years. For these states, holographic entanglement is computed by the Ryu and Takayanagi formula, which has been shown to obey all the necessary inequalities satisfied by entanglement entropy in any relativistic quantum field theory, as well as an infinite set of new holographic specific inequalities, such as monogamy of mutual information, which we show on the screen. These higher inequalities can be regarded as constraints on geometric states. The situation is certainly more mysterious when considering generic states with time dependence, for which the covariant entropy formula by Hubeny, Rangamani, and Takayanagi must be used. Are these higher entropy inequalities an artifact of static states, or do they hold for time-dependent states as well? Unlike for static states, in the covariant case, the full gravitational dynamics is relevant for understanding this question. Ingredients such as the Einstein field equations, energy conditions, and the ADS boundary conditions all come into play. In this setting, only partial results have been obtained. For example, Wall showed that the HRT formula obeys strong subadditivity and monogamy of mutual information in any space-time dimension. In 2+1 dimension, and when the bulk has trivial topology, Check and Dong proved that all the inequalities are indeed obeyed. This last result motivated our paper. We give strong evidence for the validity of all the RT inequalities for the HRT formula in 2+1 dimensions for multiply connected spacetimes. The evidence is both numerical and analytical. We ran numerical tests of these inequalities by randomly generating configurations of boundary regions in vacuum solutions, which are quotients of ADS3, and numerically computing the inequalities. The quotients we have studied are 3 rotating wormhole solutions, a BTZ black hole, a 3-boundary wormhole, and a wormhole with 1 asymptotic boundary and a torus behind the horizon. We tested millions of configurations without finding a counterexample. On the screen, we show some of the results for the 3-boundary wormhole. The histograms present the number of configurations taking a given value for the specified inequality, and the fact that no configuration gives a negative value means that all these dihedral inequalities are satisfied. As a sanity check, counterexamples are quickly found by tweaking with the coefficients of each inequality or by changing the protocol to compute the HRT entropies. We also generalized the theorem by Check and Dong to the case where the bulk has spatial topology of a cylinder, for example, the BTZ black hole. Along the way, we proved that HRT surfaces do not spontaneously break symmetries of the bulk, and this result is independent of dimension. A general proof for spacetime with more complicated topology, or for spacetimes of dimensions higher than 3, remains a very interesting open question which we encourage our readers to explore. Thank you.